We'll work several more examples about sequence convergence or divergence. This one says, does the sequence converge or diverge? It's already got it in the limit, but on the exam, they would give you this sequence and say, does this sequence converge or diverge? We're always going to try to use the limit. It's the only test we have, really, to determine convergence or divergence. Here we're going to use L'Hopital's rule because we get infinity over infinity when we plug that in. That's what we get when we take L'Hopital's rule. This is a real number value. This is a good result. This says a sub n, which is n plus the n over the quantity n plus 1, converges, and specifically converges to 1. As the terms get closer and closer and closer to the nth term, or as n tends toward infinity, the value of those terms gets really, really, really close to 1 and stays there. So that is a convergent sequence. Here's another one, again, already inside of the limit, but the nth term would be given to you as this. We'll run our one sequence test that we have, the natural log of n over n. When I plug in infinity, I do get infinity over infinity, so I'm going to use L'Hopital's. Again, please don't bring x to this party. These are nth terms, so it's going to be done in terms of n. So now when I try to evaluate this again, I get 1 over huge, which is 0. So a sub n, which equals natural log of n over n, converges, and specifically converges to 0. So let's look at our next example. Determine whether the sequence a sub n equals -1 to the n is convergent or divergent. So we'll pop that inside of the limit, -1 to the n, and I get, I'm not sure what I get. I would get -1 quantity to the huge. Well, hopefully you recognize this as an indeterminate form. When we were doing our limit work, we recognize that as an indeterminate form. What does that mean? That means we have absolutely no idea what it's doing for large input values. It could go ahead and converge to a value. It may diverge. So let's use that one. You know, there was that one tip that said we don't really care what's happening here. This is -1 to the n times 1 to the n, right? We could write it that way. And that one technique said, listen, whatever the positive one is doing, then the negative one's going to do the same thing as far as convergence is concerned. So let's look at this one. Well, this is +1 to the huge. This is still indeterminate. We still don't have any idea for large input values whether that's heading to a single value or not. This is a case where our one and only one sequence convergence test fails us. So now we're going to have to figure out other things to do. What else could we do? Well, one thing that we can do is we can try to generate some terms in this sequence and get an idea of what might be happening. Because if we can come up with an idea of what might be happening for large input values of n, then we can get an idea about convergence or divergence. So let's generate, starting with n equal 1, the first few terms in this sequence. When n is 1, that's -1 to the 1, that's -1. When n is 2, that's -1 squared, that's +1. When n equals 3, -1 cubed is -1. When n equals 4, +1. And look what's happening here. The terms for this sequence, if we wanted to put them in the n and a sub n plane. There's n equal 1, 2, 3, 4. There's a sub n equal negative 1 and 1. For n equal 1, there's our first term. For n equal 2, we jump all the way up here to a sub n equal 1, and we just keep jumping back and forth and back and forth and back and forth. I don't care how large n gets, the terms in this sequence never settle down to one value. This sequence diverges. And I could not use the limit to prove that. I had to actually generate some terms and prove to the AP reader and myself that we're not getting closer to any one single value. So there's one example of what sequence divergence might look like. So here's another one. Does the sequence converge or diverge? Again, they give us the nth term inside of the limit. And that is the first thing we're always going to run. We're going to try to get this limit to work for us. Well, the numerator is quantity negative 1 to the huge. Don't know what's going on there for sure. That's indeterminate. And the denominator is going to infinity. So depending on what the numerator is doing, that tells us about the denominator. Let's try again to not worry about the negative sign. So let's say I just got rid of the oscillating numerator. Let's say I just worried about the positive end of things. So let's say I didn't worry about the negative ones and the positive ones going on in my alternating terms. I just worried about what is that last term doing, whether it's above or below the nth axis, I don't care. Let's visualize what's going on here. So on our terms, the first term when n equals 1 is negative 1. The second term when n equals 2 is positive 1/2. The third term is negative 1/3, then positive 1/4, then negative 1/5. Do you see what's happening here as far as our subsequent terms are concerned? Our terms are getting, even though they're jumping above and below this nth axis, as n gets closer and closer and closer to infinity, they're hovering right above and right below the output values of 0. If we were graphing a function, we would say it's acting like so. So it turns out that in this case, I can actually just see what the positive sequence is doing, with not caring about the fact that we're jumping above and below our value that we're settling down toward. And this is why, if you'll look back at your notes, this is why we said we get to ignore that alternating negative 1 to the n term when that limit goes to 0. Because when that limit goes to 0, it means this is what's happening. We're hovering, yes, above and below and above and below and above and below, but we're getting closer and closer and closer to a value of 0. And in that case, that is sequence convergence. So this converges, and it converges to 0. All right, let's see if we have another example here. One last example. Does the sequence converge or diverge? Well, we could put it inside the limit, or we could also recognize what's going on with the nth term. Do you recognize that this is a geometric sequence? And remember, all we have to do when we're talking about convergence or divergence of a geometric sequence is, number 1, for the AP reader, recognize it as such, and number 2, show them that we recognize that when the absolute value of r is less than 1, as it is in this case, that the sequence converges. Now, without the limit, we can't say what it converges to. But most of the time, they don't ask you what value it converges to. They just ask you, does it converge or does it diverge? We know in the absence of convergence, we have divergence. If we can't prove convergence, then our sequence must diverge. So that's all we would need to show for a geometric sequence. And we would just need to identify R and the fact that the absolute value of R is less than 1. And we know that the sequence converges. So let me say this about sequences, because the next lessons we're going to depart sequences and we're going to start talking about series. Series are very different animals, but they are based on a foundation of a sequence. So we need to know about sequences, number one, before we can even talk about series. Plus, sequences are going to be on the exam. Series are going to be on the exam much more often, but we could have a question over convergence or divergence of a sequence. So don't forget this. Even though we're not going to talk about it often after today's lesson, it is something that you're still responsible for knowing and responsible for being able to determine. You're going to be asked a lot about whether a series converges or diverges, but you will occasionally be asked whether the sequence does. So don't forget this. All right, so that finishes up infinite sequences. Come to class next time and we'll work some homework problems.